In this video, I'm going to be working some practice problems on the second fundamental theorem of calculus, taking the derivative of functions defined by integrals. So what we need to be remembering right now is that the derivative of, the integral from 0 to x of f of t dt is f of x, and that that's true regardless of the value of that lower bound. And it does get more complicated than that. There's chain rule things to consider about what if the x is in the lower bound. Okay, but we know what to do in those situations. We're going to practice that right now. And if you're not sure what to do in situations like that, you need to go back to the lesson in the video for that one. It's very easy to understand why all this stuff is true. So just if you're having any doubts, you need to just go back to the lesson, and it will assuage you of your concerns. All right, so the first one we're going to start off with an easy one where f is the integral from 0 to x of secant t dt. Okay, so there's nothing weird going on with this one. We're just going to take that upper bound, throw it in wherever we see t in the integrand, but not the dt. And then we're going to say that f prime of x is equal to secant x. Okay, just like that. Okay, the next one's almost the same. But the upper bound is got its own derivative, so we have to be careful with the chain rule. So I'm going to still take that upper bound and throw it in wherever I see t in the integrand, but not the dt. And so that's going to be 1 over 3x plus 1. Okay. But because this is a composition of functions, really, we need to multiply by the 3 for the chain rule. So I'm going to go off to the side. The derivative of 3x is 3, so I'm just multiply that right there. If we wanted to, we could simplify that and say that's 3 over 3x plus 1, but that's not necessarily something we have to do in this class. Okay, with this one, the variable is in the lower bound of integration, and so, when we switch the bounds of integration, it makes the integral negative. So this derivative is just going to be the negative of what it would be had the x been in the upper bound. So I'm going to put in the x wherever I see t in the integrand. So it'll be x e to the x, okay, but it'll be multiplied by -1 because it was in the lower bound. Whoops. Oh, whoops. Okay, like that. And if you were to see it, I could just go ahead and say that this is the same as the negative of the integral from 4 to x of t to the t dt. And so if I took the derivative of that, it would definitely have to be negative x e to the x. With this next one, I'm going to plug in x cubed wherever I see t in the integrand. And so I'll have x cubed divided by 1 minus x cubed. And then I'll need to multiply by 3x squared for the chain rule. And if I was going to write that as one fraction, that would be 3x to the 5th divided by 1 minus x cubed. Right, when we've got both bounds variable, the integral from x to x plus 1 of t squared dt, we'll be able to deal with that, the way you would expect with a little bit of subtraction, right? We integrate regularly, it's top minus bottom, so it's going to kind of be the same way here. We're taking thing squared would be the derivative, but I've kind of got two different things going on, so it's going to be x plus 1 squared minus x squared. And I would not recommend trying to do anything else with that. I don't really see much benefit there. The last one we've got, f of x is the integral from 10 to sine x of 2t with respect to t. Okay, and so I'm going to, this is just a normal chain rule one, 2 times sine x, and then we're going to multiply by the derivative of sine x for the chain rule. That would be cosine x. Okay, so we've taken our derivatives. And now we're going to be interested in doing stuff with that. So maybe writing an equation for a tangent line. So write an equation for the line tangent to the graph of y equals 5 plus the integral from 1 to x of 2 over t minus 2 dt at the point where x is equal to 1. Okay, so I'm going to need a point and a slope, just like we always have. So the point would be x equals 1 and y is equal to, I'm not sure, oh, okay, 5 plus the integral from 1 to 1, that's just going to be 5. And then I'm going to say, Okay, doesn't really matter what's on the inside. 2 over t minus 2 dt. That's just going to equal 5. Okay, so the point is 1 and 5. The slope, I'm going to need the derivative. So I'm going to take dy dx, and that's just going to be plugging in x for t. So that's going to be 2 over x minus 2. Okay, at x equals 1, that's 2 over 1 minus 2. That's going to be negative 2. So my equation is going to be y minus 5 is negative 2 times x minus 1. Okay, that's not what I was going for, but it'll work. All right, next we might be interested in, intervals on which a function is increasing or decreasing. And in order to do that, we're going to have to take the derivative. So I see that g is decreasing. I remember that means that the derivative of g needs to be less than 0. Okay, so I'm going to take the derivative over here and say, all right, g prime of x is going to be x squared minus 100 multiplied by 2x for the chain rule. And I think I can factor that a little bit more. I'm going to call that 2x times x plus 10 and x minus 10. And at this point, you can make a sign chart. You can make a sketch of the graph. I'm going to sketch the graph. This is a third-degree polynomial with a positive leading coefficient, and it's got 3 distinct zeros. So it's going to go up and down and up like that. And then the x-axis will sit somewhere like that. And then the zeros are going to be negative 10, 0, and positive 10. Okay, and we want to know where g is decreasing, so that's where g prime is less than 0. So that's going to be through here where x is less than negative 10. And also between 0 and 10. All right, now we're looking at a picture of the graph of f, and g is the integral from 2 to x of f of t dt. Very common problem type. Okay, so on what intervals, if any, is g decreasing? So same idea here. We need to take g prime, set it less than 0. But I think I'm going to really first emphasize the derivative of g, because we're going to need to keep coming back on that, at least on parts A and B. So I'm going to say, all right, if I take the derivative of g, I'm going to get f of x. So g prime of x equals f of x. F is the derivative of g. I'm going to even write in here, this is also the graph of g prime. Because that sometimes helps. Okay, if we're looking for where g is decreasing, we want to know where g prime is less than 0. Okay, we're thinking about this especially. So I'm going to say g prime, which I know is equal to f, is less than 0 when x is between 2 and 6. Okay, and then find g prime of 4, or explain why it doesn't exist. All right, well, g prime of 4 is going to equal f of 4. And we can look on the graph. The height of the graph of f at x equals 4 is negative 2. And so g prime of 4 is negative 2. What doesn't exist is g double prime of negative 4, because that would be f prime of 4, and f prime of 4 doesn't exist because of the sharp corner. All right, find g of 8 and g of 0. All right. G of 8 is going to be the integral from 2 to 8 of f of t dt. And so if I add from 2 up to 8, all right, so the triangle has a width of 4 and a height of 2, so the area is half of 8. That's going to be negative 4. And then over here, that area from 6 to 8 is going to be 1.5, just kind of by square counting. And so I'm going to have, all right, from 2 to 8, that would be negative 4 plus 1.5, that's negative 2.5. And then g of 0 is the integral from 2 to 0, but that's backwards. So I'm going to say that's the negative of the integral from 0 to 2 of f. All right, now this is going to be another 1.5. So this is going to be negative 1.5. Okay, we can be asked to find absolute extrema of these functions defined by integrals. So let g of x equal the integral from 2 to x of f of t dt. Find the absolute minimum value of g on the closed interval negative 4 to 3. Justify our answer. Okay, so if we're trying to find the absolute maximum of or minimum of a function on a closed interval, we need to make our table and do a candidates test. That's not totally straight, but it'll be all right. So I'm going to need x versus g of x. Okay, so we're definitely considering the endpoints, but we're also going to be considering any place where g prime of x is equal to 0. Okay, we're going to need to, again, just like we did on the last one, really emphasize that we know what g prime of x is, because that's the important thing here today, and really generally in this class. This is a very important concept, that g prime of x is going to equal f of x if g is the integral of f. Okay. And then, let's see, like, extend that a little bit. And, okay, so g prime of x, which is f of x, is going to equal 0 at x equals negative 2 and x equals 0. Okay, I'm going to include both of these in my table because, you know, in the free response section of AP Calculus, we can exclude x equals 0 because it's a local maximum, provided that we explain why it's a local maximum. And for my money, I think it's going to be faster to calculate the area and put it in our table and consider it. Okay, so at x equals, okay, all of these are going to be area computations I need to make. All right, so what I think I'll do is I'm going to first kind of draw a vertical line here at x equals 2. And so I think I'll start with x equals 3. So this is going to be, that's 1.5 units of area right there in that trapezoid. So g of 3 is going to equal negative 1.5 because it's below the x-axis. Okay. Past that, I won't need that section anymore. So I'm going to just start finding areas of like triangles. And so the area of this triangle would be half of 4, which is going to be 2. This one is 2 by 1, so the area would be half of 2. And then going all the way back here, this triangle is the same as the other one, so it's going to have an area of 2 also. Okay, I'm just talking about areas right now, and we'll get to positive and negative here in a second. All right, so maybe I'll just start from x equals 2 and go right to left. That's not what we would usually do. So I'm going to say g of 0 equals, and if you are good to just say g of 0 equals negative 2, you can put that in your table. That's fine. We don't have to show this. I'm just trying to explain why I'm going to be saying, okay, g of 0 equals the integral from 2 to 0 of f of t dt. And that's the negative of the integral from 0 to 2 of f of t dt. Oh, see, I got it backwards. I always do that. And that's why I work these out that way. Because it's not going to be negative 2. It's going to be positive 2 because we're going backwards on a negative region. Okay, and this is one of the students in my class always just run circles around me on this, but that's okay. I always make mistakes on this. And so I'm going to say that this is the negative of negative 2. I'm going to confidently put in a 2 there. All right, g of negative 2 is going to equal the integral from 2 to negative 2, and we're going to go through the same process here. So it's the negative of 1 minus 2, so that's negative, negative 1, it's going to be just 1. And then g of negative 4 is going to equal the integral from 2 to negative 4. And that's going to be the negative of negative 2 plus 1 minus 2. Okay, so I've got negative 3 made negative, that's positive 3. All right, so it's going to be And then at this point, and this is based on what I saw this summer, I was grading an absolute extremum, and I don't remember if it was maximum or minimum, but a really significant number of papers was finding the wrong one, and that's, I don't want that to be you, and I also don't want you to be confused as to what's the answer. Is it like an X value or is it an output value? What is it going to be? So we need to go back in and look closer at the problem. If we go back here and look, it's a minimum value of G. So it needs to come from the output column of my table, and I need to look for the minimum. It's going to be right there. And I'm going to say the minimum value is negative 1.5. And kind of clearly indicate that that's my answer. Okay, that was a lot of scratch work that I did, but it's worth it because we need to make sure that all of the values in our table are correct. Okay, this next one, I know this problem. This one has been a tough question at my calculus class for as long as I've been a calculus teacher. This is related to a multiple choice question we have seen along the way, but it's slightly different. If g of x is equal to the integral from 0 to x of f of t dt, on what intervals is g both positive and decreasing? Okay, so the easiest way to do this one is going to be to start by thinking about the decreasing. That's what's new to us. That's what we need to work on. We're going to say, all right, if g is decreasing, that means g prime is equal to 0. Pardon me, less than 0. I'm going to think about what g prime is. G prime of x is equal to f of x. And so we're really interested in just places where f of x is less than 0. And that helps because that's the graph we're looking at. So we're really only interested in this portion of the graph right here. Okay. So I have to think about, okay, from -1 to 0 and probably beyond 0, what's going on? Because at x equals 0 is where the integral starts for g. So I'm going to go in and I'm going to say, all right, well, g of 0 is equal to 0. Because there's been no area yet. That's my first point. Then my second point is going to be when x is greater than 0, g is the integral from 0 to x, so I'm going to be counting negative area. Okay, g of x is going to be negative. Okay. And then my third point is when x is between -1 and 0, we'll have g of x, which is the integral from 0 to x of f of t dt. Okay. Or, it would not really be very typical to write it like this, but if x is less than 0, it might make more sense to think about putting the x as the lower bound of integration and 0 as the upper bound of integration, and then just think about it being negative after the fact. Okay. That is going to be the negative of a negative number, which is going to be greater than 0. If I think about integrating backwards on a negative region, if you're good with that. But that means that g is going to be positive from -1 to 0. When g is less than -1, when x is less than -1, g is increasing because it's adding positive areas as you go left to right, and so it doesn't fit our description. I'm going to say g is both positive and decreasing from -1 to 0. But that's definitely a tricky one. All right, now here's a problem from this year's free response. And, we probably did this one in class already. I know I definitely included this one in my notes this year. But, maybe in the future I'd switch up the notes and add a different example that we go back to when we're first learning about it. But even still, it doesn't hurt to say, okay, g prime of x, that's where we're going to take the x, and we're going to throw it in for t. So g prime of 10 is going to equal f of 10, which is going to be 2. And that's the reason for my answer, is that g prime is equal to f, or g prime of 10 equals f of 10. I can't remember. I graded this problem a little bit this summer, but I do think that earned both points, or the point, or whatever it was, but with an implicit connection. I always recommend a super explicit g prime of x equals f of x. Not that you have to start every sentence with it, but there's lots of opportunities to remind the reader that what's going on there, and it never hurts. So finding all values of x in the open interval -6 to 12, where the graph of g has a point of inflection. Okay, it's going to be a sign change in g double prime. But I'm looking at the graph of f, which is also the graph of g prime. And if I'm looking at the graph of the derivative and I'm thinking about points of inflection on the original, that's the extremas on the derivative because that's a sign change in the second derivative. And it's sign change in the slope of the first derivative. Same thing. So I'm going to say that's happening at -3, 3, and 6. And you could say g prime equals f has extrema. That's a really good reason. I'm going to say sign change in the slope of g prime, which I know is f. Okay, and that's reasoning against the graph that we're given, which is very important in the class that we're in. All right, g of 12 and g of 0, we're going to be just finding some areas. So g of 12 is going to equal the integral from 6 to 12 of f. And it's just going to be finding the area of this triangle. It's got a width of 6 and a height of 3, so half of 18 is going to be 9. And then g of 0 is going to equal the integral from 6 back to 0 on f of t dt, which is the negative of the integral from 0 to 6. And thinking about this half circle, let's see, it's got a radius of 3, and so the area of the whole circle would be 9 pi, and if it's a half circle, that would be 9 pi divided by 2. Okay, and if I'm taking the negative of the integral from 0 to 6, that would be -9 pi over 2. Okay, and then finding the value of x at which g attains its absolute maximum. Okay, move that over here. I'm going to need to make a table. Okay, x and g of x. We've already checked x equals 12. Okay, we're going to need to 6 to 12. I think that meant to say -6 to 12. Whoops. Yeah, because like 6 to 12, it's going to obtain its absolute maximum at x equals 12 because it increased the whole time. It's not a very interesting question. Yeah, we're going to need -6 to 12. And, okay, well, we've already done g of 12, and I'm going to fill that in. I'll come back on that in a minute. I'm interested in where g prime is equal to 0. I'm going to remind everyone that I'm well aware that g prime is f. And that is equal to 0 at x equals 0 and x equals 6. And again, x equals 6 is neither a maximum nor a minimum because its first derivative didn't change signs. But you don't want to have to go through that because g of 6 is very easy to find. G of 6 is the integral from 6 to 6 of f of t dt, which we know is going to be equal to 0. Okay, let's see, g of 0, we already did that one. That's -9 pi over 2. And so really all that's left is g of -6, which is equal to the integral from 6 backwards to -6. And we can rewrite that as the negative of the integral from -6 to 6 and integrate kind of forward. But if I think about -6 to 0, that's going to be another 9 pi over 2, but this time below the x-axis. So counting negatively, the two half circles balance each other out. So that's going to also be a 0. And so I'm going to say, okay, the minimum value, or no, maximum. I must have done minimum in class. Okay, maximum, and then I'm looking for x where this happens. Okay, the maximum's happening right here. So my answer is x equals 12. Okay, and then the justification is all the work that is right in there. All right, now for 8 and 9, we're, okay, I have two different things going on. So on what intervals is g decreasing? Okay, we can do this. Seems like we've only been finding where the function is decreasing, not everywhere it's increasing, but I'm sure that time will come. We're going to need to find where g prime is less than 0. So I'm going to plug in x for t. Okay, and that's my derivative, and I'm interested in where this is less than 0. Okay, what's going to happen here is we're going to be disregarding the denominator. Okay, I'm going to point out that the square root of x squared plus 7 is always greater than 0. First of all, because it's a positive square root. Okay, and so that's never going to be a negative number. That square root symbol, that does mean the positive square root. And I'm sorry if you've been lied to along the way, but that's what that means. And even still, I can say this for all x, because x squared plus 7 is never a negative number, okay? And it's never equal to 0 either. So this derivative doesn't have any domain issues. This is what I'm trying to say. Okay, so I'm not concerned about anything with the denominator. I'm actually just going to be considering the numerator. And so I'm going to make a sign chart on G prime. So the places where G prime could potentially change signs are going to be the zeros of the numerator, and so I'm going to need to factor that. Okay, so x times x squared minus x minus 6. I can keep going. That's going to be x minus 3 and x plus 2. And so it'll be negative 2, 0, and 3. And so I'm going to just go to each. I mean, you can test a representative from each subinterval, or you could use the multiplicities. But basically, I'm just going to plug in 1 to start with, and I'm going to have 1. I'm really thinking about plugging in 1 right there, because the factored form makes it easiest to do the arithmetic. So that would be 1 times negative 2 times positive 3. That's going to be a negative number divided by that square root, which is going to be a positive number. Okay, so negative over positive is negative. Okay, that's something I'm interested in, decreasing, right? Then the multiplicities of all these roots is 1. So I'm going to have a sign change at all of them. And that does also make sense if I think about, the shape of that third degree polynomial with positive leading coefficient, which the numerator is, and the denominator is always positive. That's not what the graph of G prime is actually going to look like because of that division. I think the graph might actually be kind of interesting. But I've got my sign chart ready. I'm interested in places where the function's decreasing, so it's going to be in these two intervals. And so it's kind of got two answers. I'm going to say x is less than negative 2. Whoops, I forgot. It doesn't like blue. And 0 to 3. All right. So if we've got g of 2 equals 5 and g prime of 2 equals 3, then the limit of the integral from 2 to x of g of t dt over x minus 2 is going to be, well, it's going to be something we have to compute with L'Hopital's rule. So I'm going to start by checking the limits of the numerator and denominator separately, verify the conditions of L'Hopital's rule. So the limit as x approaches 2 of the integral from 2 to x, I'm going to get closer to taking the integral from 2 to 2, and that's going to be 0. Okay, I think I was probably supposed to give you some disclaimer like g is maybe a twice differentiable function or something like that. But you have faith. What we're really working on here is finding the answer and justifying our solution. So limit as x approaches 2 of the denominator is also going to be equal to 0. So I'm going to apply L'Hopital's rule. And I'm going to consider the limit of the ratio of the derivatives. So the derivative of the numerator is going to be g of x, and the derivative of x minus 2 is going to be equal to 1. And that is not the limit as x approaches 0, it's x approaches 2. And so that would be g of 2, that's going to be 5. Okay, so the fact that g prime of 2 is equal to 3, that was not useful information to me. Maybe I did need that because that gives me the fact that the continuity, but this is a homework problem. It's not a huge deal. All right, moving on to, I think it's going to be the last page. Yeah. So this one is from, 2024. It's recent. This one was kind of weird. the function f was differentiable in its domain, and the area of region R was 12, which knew that, and the graph of f has a horizontal tangent line at x equals -2, and then from 0 to 7, it's actually just a line segment. Okay. So g is defined by the integral from 0 to x of f of t dt. Find these three values. Okay, we can definitely do that. G of -6, they went ahead and told us the area of R, so that'll be helpful. The integral from 0 to -6 of f, which is the negative of the integral from -6 to 0. That's going to be -12. Or you could think integrating a positive function backwards is going to give you a negative amount of area. It gives you the same result. G of 4 is going to be a triangle, so the integral from 0 to 4 of f. And that would be half of 4 times 2, so that's going to be 4. And then G of 6 is going to be the integral from 0 to 6. So I'm going to have that area, which was 4, and then this has a width of 2 and a height of -1. So that would be an area of 1, okay, which would be negative. So that would be 4 minus 1, which is 3. Find all values of x between 0 and 6 at which the graph of g has a critical point. Why wouldn't they give you the option to say -2? That's surprising. If this was my question, I definitely would have allowed for people to prove their lack of knowledge, just at the same time as they proved their knowledge. Okay, but either way, okay, we're only looking 0 to 6. It doesn't really matter. There's only one place where g prime, which is f, is equal to 0. So if I take the derivative of g, I'm going to plug in x for t in the integrand. So I'm going to say, okay, g prime of x equals f of x. And that's probably good enough. Say, okay, g prime, which I know is f, is equal to 0. That's a critical point. F is defined for all values on its domain, so there's not going to be a place where g prime doesn't exist. And then I'm going to say that's at x equals 4. And the reason for my answer is that g prime, which is f, is equal to 0. Let h be the integral from -6 to x of f prime. Okay, that's interesting. Okay, h prime and h double prime. Okay, let's start with h of 6. I don't remember working this problem. I'm sure I did when the problem came out, but it's been long enough now, I've kind of forgotten about it. So h of 6 is the integral from -6 to 6 of f prime of t dt. Okay, since it's f prime, we need to just use the fundamental theorem of calculus and not be looking at the graph, like the areas under the graph. We're going to need to look at the graph to find the values eventually. That's going to be f of 6, anti-differentiate, plug in the bounds, and subtract. Okay, f of 6 minus f of -6. Fortunately for us, we can see that we've got those values given to us. So that would be -1, f of 6, minus positive 0.5, and that's -1.5. And now, if I take the derivative of h, that would be h prime of x equals f prime of x. Kind of a weird identity, but h is going to be f, separated by a constant or something. And maybe it's probably h of x is equal to f of x minus a half is what it's going to be. But that's not what's important here. H prime equals f prime, and h prime of 6 is equal to f prime of 6. The slope of the graph of f at x equals 6, okay, we can see that, looks like it's -0.5. And that fits with the rest of the line segment where it went down by 2 when x went over by 4. Okay, so the slope is -0.5. And then h double prime of x is going to be f double prime of x. And h double prime of 6 is going to equal 0 because f is a linear function. Okay, so the second derivative of a linear function has to be equal to 0. That's where we were using that. Okay, now the last problem we've got is, let's kind of just put all of the pieces on the table, increasing, decreasing, concave up, concave down, maximum, minimum, point of inflection. Okay, so f of x is the integral from 1 to x of g of t dt. I think what I'm going to do is give a reason for each answer, and if you do not want to, squeeze all of that in, that would be understandable. Okay, so g is increasing, and we're looking for when. Oh, that's silly. Those want to be f's. All right. Well, if I'm gonna have one error in the homework, I might as well have two, and go back and fix the PDF. And hopefully, by the time you're viewing this, the copies I ran this year, they're already run. But in the future, I'm sure the homework will look right. So f is going to be increasing. We need to talk about f's derivative. So f prime of x is equal to g of x. And we're eventually going to care about the second derivative as well. So I'm just going to point out that f double prime of x is g prime of x. I'm also realizing if I'm going to try to write a reason for my answer, I'm going to need to get all of this stuff out of here. Okay, so I'm going to start in with increasing. And okay, so increasing would be when it's positive, so that's when 0 to 3, and maybe I'll just say x is less than 3. Oh, I'm going to just change it so that the domain of f is 0 to 5. Let's just do that. So, okay, less than 3 and greater than 4, or 4 to 5. On those intervals, because the first derivative is positive. I'm going to come back and write in all the answers afterwards. F is decreasing when the derivative is negative, so the graph of g, that's, okay, 3 to 4. F is concave up when its first derivative, g, is increasing, so that's 1 to 2 and 3.5 to 5. Concave down would be when the first derivative of f, which is g, is decreasing, so 0 to 1, 2 to 3.5, and that's it. 0 to 1 and 2 to 3.5. All right, it's going to have a local maximum where its first derivative goes from positive to negative, and we're looking at a picture of the first derivative. First derivative goes from positive to negative at x equals 3. So at x equals 3, minimum is going to be where the derivative goes from negative to positive. That would be x equals 4. You can even see that in the increasing and decreasing behavior if you think about it. And then also points of inflection would be where the concavity changes. You could look at it that way. Or you could say these are going to be the extrema, or the places where the sign of the slope of f prime changes. So this is going to be x equals 1, x equals 2, x equals 3.5. You could probably say x equals 5 if you saw that. It's no big deal. It doesn't really matter. Has points of inflection at, I said 1, 2, 3.5. Kind of like that. Now, if I want to go in and give reasons for my answer, okay, I'm going to say, using the graph that I've got, that's going to be basically f prime, which is g, is positive. Here, say decreasing is where f prime, which I know is equal to g, is negative. For concave up and concave down, looking at the graph, what we saw was the increase-decrease behavior of the first derivative. So I'm going to say f prime equals g is increasing. For concave down, I'll say that it was decreasing. a maximum is where the graph went from positive to negative. So I'm going to say f prime, which I still know is g, went from positive to negative. Okay. X equals 4 is going to be the opposite. The derivative went from negative to positive. And then points of inflection, that's when we have to be careful. I'm going to say the first derivative had extrema. The other time we talked about points of inflection, I was talking about the sign of the slope change. That's a valid option as well. They both work, but we have to be reasoning against the graph we're given. So I'm going to say the graph we're given was the first derivative of f, which is g, has local extrema. All right, that's all good set of problems. A whole lot better than the old set of problems I had, and way better than the original set. That was one of my worst homeworks ever. And so I think this is a lot closer to what you need in the long run for AP Calculus, especially with these graph problems. It's a very common free response problem type. And there's also a lot of multiple choice questions that go off this topic. So this, the second fundamental theorem of calculus, this one's really important for us in our overall calculus development. So it's good that we did this good solid set of problems. That's going to be all for this video. Thanks for watching.